Hello everyone and welcome back to lecture 7. In this part of the lecture we are going to talk about effective temperature driving force and how that driving force depends on the flow pattern of the fluid in the heat exchanger and how we can actually correct for this driving force when we are talking about a very complicated flow pattern. Okay, so let's consider a shell and tube heat exchanger, and one of the most simplest form of shell and tube heat exchanger, that is actually what we call a double pipe heat exchanger. Okay, and in this double pipe heat exchanger we have a tube where the fluid is flowing. Let's say the hot fluid is flowing inside the tube, and then the cold fluid is flowing outside this tube in the shell, and the two fluids exchange heat with the wall of the heat exchanger, and then we have the heat exchange. So if you look at this, for example, flow situation, we can have either a parallel system in which the two fluids are flowing in the same direction. So the shell fluid is going in this direction, and so is the fluid in the tube. This kind of arrangement is called parallel flow or co-current flow arrangements. While you can have a situation where the two fluid is moving, for example, from left to right hand side, while the shell fluid is moving from right hand side to the left hand side. So they are in opposite direction. And this form of flow is called counter current flow direction. Okay. And the reason we are talking about this because these are going to affect what kind of driving force is available inside your heat exchanger. So let's first look at pure parallel flow. Okay, so it means that there are two fluids involved and one fluid is going in this direction. For example, the hot fluid is going in this direction and the cold fluid is also going in the same direction. So if you look at this situation, you see that for the case of hot fluid, so it enters the heat exchanger at a temperature Thi, and as the fluid moves along the length of the heat exchanger, it loses its temperature to the cold fluid. Okay, and as such, it drops its temperature from Thi to Tho. While for the case of cold fluid, we have it enters at the heat exchanger at a temperature of Tci, and it gains heat from the hot fluid, and the temperature of the cold fluid at the exit point is higher than that of the entering point. Okay, and the reason this temperature profile is very important because it gives us information what is the available delta T in a heat exchanger over this length scale of L. So here if you see that you have a temperature gradient, quite high temperature gradient at the beginning of the heat exchanger, but as you move along the length of the exchanger, the temperature gradient becomes less and less. Okay, so when we are working with parallel flow or co-current flow, we have to be careful what is the minimum delta T available, because we don't want to go below 10 degrees centigrade, and that is mostly the minimum allowed delta T for design. Okay, so you will take a course next semester, actually in year 2 semester 2, that is related with heat recovery and optimal design of heat networks. And when you do that kind of analysis, that is called pinch analysis, you define a minimum delta T, and as such, you design all your heat exchangers with a delta T above this minimum delta T. Okay, so you have to be careful that we don't reach a situation where the delta T between two fluids become less than the minimum allowed in the heat exchanger design. For the case of pure countercurrent flow, so here you have slightly different situation. So the hot fluid, let's say, is going from left to right, while the cold fluid is going from the hot fluid is going from right to left, and the cold fluid is going from left to right. So they are in opposite flow pattern. And if you plot again the temperature on temperature length profile, we can see that the Ti is the temperature at the inlet and Th0 is the temperature at the outlet. And if you look at the temperature profile in terms of the delta T available, you can see that for this profile, the temperature difference is more or less constant over the length of the heat exchanger. Okay, So for the case of counter current, we have less issue with delta T availability because we can see that it's more or less constant. So whatever delta T we define as the minimum delta T, we can just make our delta T available above that. Okay. So that is one of the reasons why we use counter current flow in most of applications. Now we can have also some situations where one of the fluid is actually a constant temperature fluid, and by a constant temperature fluid, you can have where the temperature is not changing over the length of the heat exchanger, and that could be, for example, a condensing vapor. So in your booklet in section 7.12, figure 7.3, there are some other cases where you can have different temperature profiles depending on the flow pattern and the fluid nature. So please have a look at that. So what we discussed so far is one of the easiest case where you have pure countercurrent or co-current flows. It means that you have a shell and tube heat exchanger with only one shell and one tube. Okay, so that is the simplest case of shell and tube heat exchanger. And we defined the temperature profiles in the previous slide, but in reality, you can have much more complicated situations because these one shell and one tube heat exchanger is not going to serve you in actual life because the heat exchanger duty available through this heat exchanger is too low. So you have to adopt more complicated configurations. So here we have an example of, again, a relatively simple case. So you have one shell and you have two tube passes. Okay, and if you try, so let's say you have the cold fluid is moving, sorry, the hot fluid is moving in the shell. Okay, so that's the hot fluid, and the cold fluid is moving in the tubes. If you look at the temperature profile and you try to draw it, you see that the hot fluid is losing heat as it moves along the length of the heat exchanger. Okay, while the cold fluid is, for example, when you move along the first pass of the tube, like you are moving in this part. Okay, and you can see that the flow pattern is co-current, and then you reach the end of the tube pass and then you enter the second tube pass, and now the flow pattern is countercurrent. Okay, so you have now a situation where you have both co-current and countercurrent flow, and that complicate your situation in terms of what is the delta T available. You can have even more complicated situation when you are talking about several passes. For example, in one shell you can have multiple passes, like 4 multiple passes or 8 multiple passes. It means that you have a shell with 8 tubes, for example, 1 2 3 4 5 6. So here, for example, I showed you 6. Similarly, you can have situations where even more complicated. Then you can also have heat exchangers where you have cross flow. So here, for example, the two fluids are moving in perpendicular direction, and along the length of the heat exchanger, they are meeting on several points. And each of these points, if you try to draw it on temperature length profile, you will see that it is very complicated how to draw all these points on that diagram. Okay, so in these complex situations, how we can calculate the driving force. Okay, so one way to calculate the driving force is by using what we call LMTD. Okay, so what is this LMTD? It comes from this equation here. We know that when we are talking about heat exchange across the surface, we use this equation of Q is equal to UA delta T, where Q is the heat rate of heat transfer, U is the clean or actual heat overall heat transfer coefficient, A is the surface area, and delta T is the temperature difference between 2 points. Okay, so if you write it in the form of a hot and cold, so you can write delta T as TH minus TC. Okay, but now when you have only 2 points, so you have one hot point and one cold point, so you can easily calculate what is the delta T. But when you have a length of different points, so for example, when the hot fluid is moving, let's say in this direction, cold fluid is moving in this direction, and over this length of heat exchange, the delta T is changing between each point. Okay, from point to point, the delta is different, and that's why we need to calculate an average value of delta T, okay, over the whole length of heat exchanger, and that delta T over an average delta T over the length of heat exchanger is what we call log mean temperature difference. Okay, so this log mean temperature difference can be represented by LMTD, or in some books you will see delta TLM. Okay, so these are both the same things. And now just to help you understand that how we can actually calculate this LMTD, so let's look at again a situation where you have, let's say, one shell and one tube. So you are again in a double pipe. Okay, so the hot fluid is in the shell of the heat exchanger. So you have T in going in and T out coming out, and then you have the cold fluid going in the tube, TC in and TC out. Okay, and in this process the heat is being exchanged from the hot fluid to the cold fluid. Okay, so let's look how we can calculate delta T over this length scale of, let's say, L. Okay, here L is the length here. Okay, so let's say we are looking at this temperature enthalpy diagram for counter current heat exchanger. The two fluids are moving in the opposite direction, and for the case of cold fluid, it is going from a low temperature to a higher temperature. Okay, so if you define two delta T's on each side of the heat exchanger, let's say where the hot fluid is entering, you are defining delta T1 is equal to TH in minus TC out, and on the exit where the hot fluid is exiting, you are defining another delta T2, and that is equal to TH out minus TC in. Okay, so what are the delta T's available between hot and cold fluids on two ends of heat exchanger? And if you now put for a pure countercurrent flow, if you put the value of these delta T's that you define on slide in this equation here, delta T1 and delta T2, so you can calculate LMTD, that is the average temperature over the length of the heat exchanger, and we call it log mean temperature difference. Okay. So now the question is, okay, we are defining our heat exchanger temperature difference by using log mean temperature difference. So why not we are using a simple arithmetic mean? So we can use the arithmetic mean temperature difference as well. Okay, but if you use arithmetic mean temperature difference, your results will be less accurate compared to LMTD, because that gives you a much more accurate average temperature over the length of the heat exchanger. So the cases where we use arithmetic mean temperature difference is when you are doing a simple calculation, a hand calculation, and you don't want to calculate logs of these temperatures, you just take the average. So in that case, we just want to give an approximation of your delta T, so we use arithmetic delta T. And the other situation can be when the two fluids that are involved in the heat exchanger and their fluid temperatures are not changing from the entrance to the exit. Okay, so in that case, delta T a arithmetic mean will be more or less as accurate as the case for LMTD. Okay, so these are the two situations where you can use delta T arithmetic mean temperature difference, but in almost all cases, we always prefer to use LMTD. Okay, so let's look at how we can define LMTD for two different situations of flow. So here we are assuming, again, we are in pure flow situation. So where we have, let's say, for the pure parallel flow, the two fluids are moving in the same direction. And again, we are looking at just one shell and one tube. Okay. So if you define again your temperature length scale graph, so you can draw the temperature profile like this. And again, you define your delta T1 and delta T2 on the two ends of heat exchanger. And then you have the values here. And if you put the values in this equation at the top, you can calculate what is your log mean temperature difference for parallel flow. Okay. And the proof of this, for example, system, or how to calculate derive the expression from delta TLM, I have provided in the slides. I'm not going to go through it because it is not important for your exam point of view. But if you want to have a look how we come to this expression of LMTD, please have a look. It's only by doing energy balance between a cold fluid and a hot fluid. Okay. Now let's look at the case of LMTD for countercurrent heat exchanger. So again, you define your temperature profiles, okay, and then you define delta T1 and delta T2 on the two ends of heat exchanger. And if you know the value of delta T1 and delta T2, again, you use the same equation and you can calculate what is your LMTD for a countercurrent heat exchanger. Okay. So as I said that the equation that we used previously for LMTD is only applicable for pure parallel flow and pure counter flow arrangements, okay? And we can write the expression here. And one thing to notice is that we use, for example, this equation for our calculation, but if you use this equation, you will get the same results. The only thing is that if you are using delta T2 first, then the delta T2 should be also at the top of the fraction when you are calculating the log. Okay, so please try to notice the difference between the two and what are the similarities here. Okay. So we define LMTD for pure parallel and countercurrent flow, but what if we have a practical situation where you have much more, for example, complicated flow arrangement or tube configuration? Let's say you have multiple tube passes or you are in a coarse flow. So LMTD is not appropriate for that because again, just to emphasize that LMTD is only calculated when you have only one shell and one tube pass for a pure countercurrent and pure parallel flow. Okay. So if you have, let's say, a much more complicated situation, let's say you have 10 tube passes or 8 tube passes, so what we can do that? We can definitely drive the temperature driving forces based on very complicated math or using softwares, but there is a simple approach that we can use to calculate what is the correct temperature difference. And to correct the temperature difference, what we do is that we multiply LMTD that we calculated for a countercurrent and co-current situation with a correction factor Ft. Okay, so this correction factors, by multiplying it with LMTD, we get the correct delta T of the heat exchanger. So this is what it means, what I said in the previous slide. So you have now Q, let's say you have a very complicated configuration with 4 tube passes, and then you have Q is equal to UA delta T correction. And to calculate delta T correct, first you have to calculate what is delta T LM, so log mean temperature difference, assuming that you are in pure countercurrent and co-current situation. It means that you have only one tube and one shell pass. And then you multiply this LMTD with Ft, the correction factor, to get the actual delta T or the driving force of the heat exchanger. So how we can calculate this Ft? So there are a lot of graphs available, for example, that people have built by using experiments, okay? And in your booklet in figure 7.5, these graphs are available, so please have a look. And these graphs are specific to a situation, for example, a type of heat exchanger and what kind of fluids are involved there. Okay, so let's have a look at these graphs. And these are how the graphs look like. Okay, and as you can see that these graphs are for a specific, like this graph on the top is only for one shell pass, while you can have 2, 4 or 6 any multiples of 2 tube passes. Okay, and to calculate the value of Ft, you need to define some temperature fractions, that is R and P. And in some cases this R and P is also called S and R. Okay, so in some books you have one kind of notation, in others you have the other one, but there is no need to worry about, because these figures always have the definitions of R and P defined on the figure itself. Okay, so if you look at the P, for example, so that is the ratio of the temperature difference between the cold fluid and the temperature difference, the maximum driving force in the system. So capital T is the shell side of the temperature and lowercase t is the tube side of the temperature. Subscript 1 is the inlet and subscript 2 is the outlet. Okay, so if you look at this definition now, it will be the temperature difference at the entrance and exit of the cold fluid divided by the maximum driving force available for cold and hot stream. While you look at the value of R, you see that again it is the temperature difference between the shell fluids. Okay, so the hot fluid, for example, or the cold fluid, and then you have the temperature difference of the fluid that is in the tube. Okay, P and R. Okay, and you can see that these pink lines, they represent different values of R, and then you use the value of P on x-axis to find a value of let's say R, and then from there you use the y-axis to calculate the value of Ft. Okay, so if you change your flow pattern, or if you change your flow configuration, the number of tubes or number of shells, for example, here now you have 2 shells and 4 tube passes, so you cannot use this figure. You have to use the figure that is experimentally, for example, drawn. And then again, you use the same analysis. You calculate P and R. You use the value of P, goes to the curve that represents your value of R, and then from y-axis you get the value of Ft. Okay, so this is how we can calculate what is the corrected delta T for even a complicated configuration. Okay, so we just calculate Lm delta T for the case of counter current or Q current situation, and then we multiply it with Ft, the correction factor, to get the corrected temperature difference. Okay, so that is all for this part. Thank you so much for your time.